Have you ever wondered how airplanes manage to fly? A Boeing 747-400 has a maximum takeoff mass of 875,000 pounds. This is about 397,000 kilograms. The Earth exerts about 10 newtons of gravitational force downwards on an object for every kilogram that object weighs, assuming that object is on Earth. So there exists 397,000 kilograms times 10 newtons per kilogram, or 3,970,000 newtons of downward force on a Boeing 747-400 at maximum takeoff mass. How on earth does it ever get off the Earth? Well, according to Newton's second law of motion, sigma F equals ma, where m is the mass of an object, a is the acceleration of the object, and sigma F is the net force being applied to the object. But in this case, the form a equals sigma F over m is going to be more useful because it tells us that acceleration is dependent and directly proportional to force. In other words, in order for the object, in this case a plane, to accelerate upwards and fly, there must be a net upward force acting upon it. Remember, there's already the downward force of gravity acting on the plane. Whatever this upward force is, it needs to be large enough to counteract this downward force and lift the plane upwards. So where is this massive upward force coming from? Well, planes have wings. Wings are, as you can imagine, pretty important in this whole flying business. The shape of an airplane's wings is ingenious. If we look at a cross-section of a plane's wings, we can see that they're curved at the top and flatter at the bottom, and this is the key to it all. When a plane takes off, it starts accelerating down the runway, which forces air to rush past the wings. When air hits the wings, it has to go around them. Obviously, it can do this by going over the top or going under the bottom. No matter what route the air takes, though, it all converges at the end of the wing at the same time. What happens is, since the top part of the wing is curved, the air that takes the top route travels a greater distance than the air that travels the bottom route. But again, the air all converges at the end of the wing at the same time. So that means that the air taking the top route actually has to be at a higher speed. Speed, after all, is just distance divided by time. If the time taken is the same between both routes, but the distance is greater in the top route, the air taking the top route has to be traveling faster. This difference in speed generates a difference in pressure. This is described in a concept called Bernoulli's principle, which is really just the law of conservation of energy applied to fluid motion. By the way, yes, air is a fluid, both gases and liquids are fluids. I'm going to simplify things a bit here, but according to Bernoulli's principle, when speed is lower, pressure is higher. When speed is higher, pressure is lower. Now, this might seem counterintuitive at first, but this actually makes a lot of sense. Imagine we have a tube that changes diameter with fluid passing through it. Now, we know that the rate at which fluid passes through the tube, that is, the volume flow rate, has to be constant throughout the tube. In other words, if, say, a liter of fluid passes through the thicker part of the tube in a minute, then a liter of fluid also passes through the thinner part of the tube in a minute. This has to be the case unless the tube is leaky or something weird, which it isn't in this scenario. But in order for the volume flow rate to be constant throughout the tube, that would have to mean that the fluid in the thinner part of the tube is moving faster than the fluid in the thicker part of the tube. Okay, but then how is this fluid moving slower in one part of the tube than in another part? Well, how does anything change speed? Acceleration. The fluid had to have accelerated. This would mean then that a net force had to have been acting on it to cause it to accelerate. Remember, A equals sigma F over m. If there was an acceleration, there had to have been a net force. This net force would have to have come from a difference in pressure between the two parts of the tube, which would mean that, indeed, the fluid that's traveling slower in the thicker part of the tube is under higher pressure than the fluid that's traveling faster in the thinner part of the tube. This simply has to be the case, otherwise there's no way for the fluid to have accelerated in this direction. When speed is lower, pressure is higher. When speed is higher, pressure is lower. The air taking the top route is at a higher speed and therefore a lower pressure than the air taking the bottom route. This pressure differential is enough to exert an upward force on the wings of the plane that's strong enough to lift the plane upwards. We can use this information to explain an airplane's stall. This happens when a plane's wings are tilted upwards at too high of an angle. When this happens, the top and bottom airstreams start separating from each other, and suddenly what was once a smooth flow of air becomes chaotic and turbulent. The lift force keeping the plane up greatly decreases, and the plane essentially free falls from the sky unless a pilot takes corrective measures. So, the next time you're hopping on a plane to your favorite vacation destination, kick back, relax, and appreciate the physics that's carrying you across the skies.